everyone, and welcome to our last MCATS seminar of the year. Thanks very much for coming. We will make an announcement about next year's plans at some point in July, we think, so look out for that. Today's speaker is Juan Meleiro, and he's going to talk about towards modular mathematics. And just to remind you, if you have any questions, please type them in the chat just to me, Eugenia Cheng. And if it's a clarifying question about something in that part of the talk, we'll stop and I'll transmit those at the end of each section. But you're welcome to type general questions in at any time, and then I'll transmit those at the end. Great, thanks very much.
Should I start?
Mm-hmm.
Well, hi. First of all, I'd like to thank the organizers for creating such an amazing space where me and my colleagues can share our ideas, being young researchers. And I'd like to thank Eugenia Cheng for helping me creating the slides and the presentation, and obviously my advisor for helping me creating the content for what I'm going to tell you. And here's a brief summary of what I'm going to talk about. I'm going to just introduce some observations about what I'm talking about, or where do I stand, just so you know where I'm coming from. Then I'm going to introduce the idea of synthetic reasoning, why it's a good thing, why it's an attractive idea, and some of its shortcomings. Then I'll talk about universal logic as a way to structure what we've seen so far and to create something new. That something new will look something like what I'm going to talk about in formal framework, the first section. And then I'll just show what it means to do modular mathematics in uses, just to give you an idea of what I mean by that. Briefly, my goal in this talk is to explain what I mean by modular mathematics, and perhaps you'll find that interesting. So here are some observations. First of all, I have an assumption. It's part of my mathematical experience, the way I was educated, what I have studied, and it's that formalizing is a good thing. Not in the sense that all mathematics should be formalized, but in the sense that mathematics that's more easily formalizable is a better thing. If we do mathematics in a framework, in a language that allows itself to be formalized in a proof assistant, that's a good thing. This is just an assumption. You might not agree with it, but perhaps that will help you understand where I'm coming from. There are two observations about mathematics which I find fundamental in the way I think about these things. And it's that I'm a logician, so I look to mathematics through a logician's eye. For me, everything is a model, which means, as I'll show in the section about synthetic reasoning, every subject area in mathematics has a particular logic to it. And in a formal sense, it has one system, which is a logic that best describes that area. And that area should be in some way a model of that logic. Obviously, you should be able to interpret that logic inside of that area. And just to be clear, what I think about as a model is really translation, a special kind of translation of logics. Because, for example, in undergraduate times, I began studying what is models of set theory. And I was always kind of annoyed by the fact that we construct models of set theory inside of set theory. So it seemed like a circular thing to me, like where are we taking the objects from? If we are trying to interpret the logic inside of itself, if you know a bit about model theory, you'll know what I'm talking about. But that's just my understanding of things. And then, what do I mean by modularity? It's just the usual sense of the word that comes from design and programming, which is the ability to construct systems in discrete modules that interact with each other through their interfaces, and which we can combine and transform to create new things. So that's it. That's the that's the philosophical underpinning of the talk. Let's talk about synthetic reasoning. What is synthetic reasoning? Well, the term probably originates in this sense in works of Koch in 81. The book is called Synthetic Differential Geometry. There he says, he's talking about differential geometry, but there he says about synthetic reasoning that what is meant by synthetic reasoning, it deals with space forms in terms of their structure, i.e. the basic geometric and conceptual constructions that can be performed. So we're talking about structure, that magical word that often means category theory to most category theorists. But in a general sense, means to deal with objects not through their internal details, but how we can interact with them, what can we do with them, how can we map out or into them, etc. And then he says, and this is the point I was talking about, everything being in a model. Generally, investigating geometric and quantitative relationships brings along with it an understanding of the logic appropriate for it. That this is the key term, the logic appropriate for it. So if you analyze a particular subject area in mathematics, you will be able to come up with a particular logic for it. And that area should be a locus of interpretation for that logic. So the slogan is structure and logic. That's the point of synthetic reasoning. What does it look like in practice? Let's compare an analytic approach to a synthetic approach for something simple, like defining derivatives. First, to define derivatives in an analytic way, we start usually with a set theory. Then we do a bunch of set theory, a lot of set theory, just so we are able to construct the real numbers. Then when we have the real numbers, we consider the functions from the real numbers to themselves. And we define the notion of a limit using formulas such as this. Then we define continuity of a function. Mind you, we're trying to define the derivative, but we have to talk about all of those things. Then we define differentiability of continuous functions, which is not the derivative. This is a formula which has the form of a universal quantifier and an existential quantifier. To turn that into a function, then we have to use the axiom of choice and do some magic to transform that into a function. So it's a lot of steps, and the important point is that most of these steps have nothing to do with derivatives, nothing to do with the fundamental behavior of derivatives, which one could argue is the chain rule and product rule, etc. In contrast, when we are doing synthetic mathematics, we would proceed something like this. This is the original way Koch does it in his book, 81 book, which is we start with a ring. We assume that we have an object, R, which is a ring. This is supposed to be interpreted inside of a category with rich structures such as a topos, but you can also think of it as a type theory. Then we define this object D, which is fundamental. It's the set of nilpotent infinitesimals inside of R, which are the points who have a null square. Classically, this is trivial, but we are doing it because it's supposed to be interpreted inside a topos in an intuitionistic way. So this is actually not provably trivial, and it's quite interesting. We postulate the following: if we have a function with an infinitesimal domain going into R, the ring, then it's of the form presented here. It's linear, which means it has a well-defined slope, and that's it. Because you see the value of A is already defined. It's just f of 0, right? And then we're done. We can create the derivative of a function applying the axiom to if you have a function f, the function f of x plus d. It's just the intuitive way we think about derivatives. If you move about a point, then then the function will move according to a linear behavior, which has a particular slope. And because we are doing it intuitionistically, the statement that this exists is the same as having a function that does it. So it's quite simple, and everything we're talking about basically has to do with derivatives or similar subjects. And then the magical thing is that we can do a lot more, much more quickly. So we can define, for example, tangent vectors as curves, infinitesimal curves, the tangent bundle, the tangent spaces, and start doing differential geometry from the get-go. And one important thing is that this is not the only way to do differential geometry in a synthetic way. In 2016, Koch presents as another work, a lecture he gives, which is transcribed and is available on the archive, where he talks about some other way to formalize differential geometry in a synthetic way. There, he disagrees with himself from years before, and he says that actually the fundamental thing in differential geometry is not a ring, but it's the proximity relation. So we start in a type theory, supposing that every type or space comes equipped with a proximity relation, which I call tilde M. It's kind of like it was a term with this type. Then we can define, for example, the kth order proximity relation, the monad, the kth order monad around a point, which we can use to talk about differentiable functions, morphisms, and etc. The details are not important. What I'm trying to show is that this is open to discussion. He says, it is not the intention of synthetic differential geometry to avoid using the wonderful tool of coordinates. The reason we did not start there is to stress that the arithmetization in terms of a ring is a tool, and not the subject matter of geometry. In particular, geometry has a life without the ring R of real numbers, who sometimes think of themselves as being the owner and boss of the company. Why am I showing this? It's because I don't like the real numbers. No, it's because I want to show you that one can discuss what is the appropriate way to talk about a particular mathematical subject. It can be critical to mathematical practice. This is the slogan. There are many ways to synthesize a subject. And it's not restricted to geometry. Here, for example, it's a work from Bauer from 2006, where he constructs a system of synthetic computability theory. He starts with a type theory, and he assumes the natural number, constructs the type of monotone sequences and a bunch of types of truth values, and then he derives a bunch of theorems, important theorems for computability in terms of these objects. Again, the details are not important. The only thing is that synthetic reasoning is not restricted to a particular subject. In sum, synthetic reasoning involves structure and logic. We're talking about the structure of objects, and we use logic to do it. And there's a rich field of possible synthesizations of an area. We can discuss it. It's open to critical discussion. But there are some issues. The most important one here is that this is really artisanal. To build a synthetic theory, you need to be a specialist, and you need to analyze the subject from the ground up, and you need to build theories from scratch. And we have no real tools to help us build those theories. You have to do it like from your own creativity. And perhaps we can fix that in some way. Before continuing, I'd like to ask, is there any clarification questions?
No, there aren't any questions at the moment. Thanks.
Great. Okay. So here we come to universal logic, which I argue is the way we should think of organizing synthetic reasoning. Universal logic is a research program, so to say, in logic, which is motivated, in my view, by this idea, which I'm going to quote. Logic is often informally described as the study of sound reasoning. an enormous development beginning in the late 19th century, it has been found that a wide variety of different principles are needed for sound reasoning in different domains. Again, recall the logics adequate for particular mathematical areas. And a logic has come to mean a set of principles for some form of sound reasoning. But, and here's the important point, in a subject, the essence of which is formalization, it is embarrassing that there is no widely acceptable formal definition of a logic. I'm not trying to argue this is true or that if you are a logician, you should agree with this. It's just I'm illustrating for those who don't know what a universal logic is. What is the motivation? There are a huge variety of logical systems that have risen in the recent decades, and we have to. Logicians are kind of logicians like to organize things. So universal logic is the effort to organize logics in a formal framework, in a way to make that clearer. Anyway, these are the main questions of universal logic: how to identify, translate, and combine logics. Identification is essential. It doesn't just mean how do you tell if two logics are the same. For example, let's say we have two formalizations of classical propositional logic using different connectives. Are those the same logic? You could say that they are because they have the same theories up to translation. But the point is that trying to identify two logics means understanding what is an essential feature of logic. Is it the syntax, or is it the deductive relations? What is it? That's the question. Translation is about, well, what does it mean to translate logics, especially when one does not have a uniform way to talk about syntax? I mean, it's fairly obvious how to translate propositional logic inside of first order logic, but there are more there is a variety of ways to talk about syntax, and it's not obvious how to translate all of them. And combination of logics has to do with how can we take features from different logics and combine them into a single system? Like I have propositional logic, and I can extend it with modalities or quantifiers. But what does it mean to extend with them both at the same time in a coherent way? That's the question. So why is this important to organize synthetic reasoning? Well, because I'm saying that synthetic reasoning has to do with particular logics that we build for particular subject areas, and universal logic, the answers to these questions will allow us to work with these logics in a more effective way. So just to be a bit more concrete, well, what could a system for universal logic look like? I have an example, which are categorical sketches. I'm not saying they are a good system, I'm just saying they're a good example. So categorical sketches are a way to formalize the idea of syntax and semantics inside of category tree. So a categorical sketch is given by a diagram, a category, and on top of it, a set of cones and a set of co-cones in that category. What does that mean? Well, the diagram will give a shape for a theory, and the cones and co-cones will give the properties, the axioms of that theory. This is made real by the notion of a model, which is a functor going from that category to another, taking the cones to limits and the co-cones to co-limits. So let's look at an example to make it more concrete. Again, this is just to illustrate what framework for universal logic could look like. A sketch for unitomagmas, the theory of unitomagmas. A unitomagma, by the way, is a type with a binary operation and an unity. It's given by this category. Actually, the category generated by this diagram under the relations on the right, which are usually expressed using other diagrams inside of the category, inside of the main graph, but that gets unwieldy fast. there are some cones making the pi pairs here into projections. So you see, I put the names of these objects in quotes because they are not really products. They are just placeholders. And the cones are saying that this should be a product in a model, but not here. Anyway, what's the point of the sketch? The point is that if you take the models of this sketch inside of the category set, then you get the category of unit amalgams, because obviously there's a notion of morphism sketches, which is not relevant here. But this is an important theorem, which relates what is translation and combination. And it's that if you take the models of a sketch inside of a category, you get a category. And then if you take the models of another sketch inside of that category, then it's the same as taking the models of the kind of combined sketch inside of the original category. So model taking is monoidally closed, and models are functors. You see, the way we define the models is that it's a functor coming from the syntactical category of a sketch into a semantical one. And there's a kind of monoidally closed structure. You can play with combination and translation. Are there any questions?
Yes, there was a question in the chat. It might have also been answered in the chat, but I'm going to just ask you anyway. Someone said, could you remind us what a cone means, or tell us what a cone means?
Yeah, sure. Inside of a category, a cone is, how can we quickly define it? It's something which has a base and a vertex, which is a diagram. Let's say you start with a diagram inside of a category, which means a functor coming from a tiny category into another category. Then a cone is another object with arrows going into every object of that diagram, such that all of the triangles commute. So, for example, for a product, maybe I'm getting the directions wrong because the cone is just inverting the arrows. If you take a product, it's the tip of a cone, right? And you have arrows going into each of the factors, and it commutes with all of the arrows in the diagram, which are known. But if you have some arrows, then you have a limit. It's the same thing. So it's just a way, it's just the general way to talk about limits and co-limits. A limit is a limiting cone, and a co-limit is a co-limiting, it's a limiting co-cone or whatever. Is that answered?
Thanks.
Okay. So that's universal logic. We have synthetic reasoning on the one side and universal logic on the other. And I'd like to join them. How can we do so? Well, I have an idea. There's this formal system called MMT, which was introduced by Florian Rabe in 2014, circa 2014, and which I think is a good candidate, perhaps a modified version of it. Let's take a look of how it looks. So in MMT, we're building a category of theories. As I was saying, I want to be able to manipulate theories and combine them and translate them. So we constructed a category where the objects are theories. A theory is just a sequence of declarations. Declaration is an identifier and an expression built from previous declarations and constructors. This is just a formalization of the way we do mathematics, actually. We start by defining objects, then postulating axioms, then proving theorems and declaring new things. And all of the declarations depend on the previous ones we have built. I'll give an example. The theory of a monoid is given by, for example, this sequence. It starts at the top and ends at the bottom. We start by declaring a type. When we declare a type, we are saying, look, when we want to talk about a single monoid, we need a type of its points. And we need a product between points of that type. So see, the expression on the right depends on the declaration that came before. And so on. We have a neutral term and some laws. Here, you can see that the structure of a monoid and the axioms are unified as a single concept, which is declarations. And the arrows and the dependent functions and equality are all part of a language we have defined before, which is called a logical framework, which is not relevant again. The point is that we have theories that can capture some mathematical object. You can think of a theory as a signature or a kind of interface. For something to be a monoid, it needs to implement this interface. But you can also think of it as a synthetic theory, like these are the main features of a monoid, the essential features of a monoid. There are morphisms between theories, which will take the place of translations. To translate a theory into another, you take every declared identifier of the first theory, and you associate with a term in the other theory that has such that this translation preserves types, actually preserves translated types. Let's look at an example again. If we want to interpret monoid as, for example, the monoid of the end of functions of a particular set in some set theory or type in a type theory, then we'll say that the type M, which is the base type of the monoid, will be interpreted as the composite expression, which is the functions, the type of functions from X to X. And as you see, when I interpret the product as composition, the type of the composition is not the type that's originally in the monoid, but the translated type, when we replace every instance of the previous terms by the expressions to which they are translated. And I think this is really beautiful because the structures of a mathematical theory, they go to structures on the other side. And the axioms, the names of the axioms go to proofs, right? Because a term of the translated type, which says that for every X, Y, and Z, or product is associative, it's just a proof of associativity under the Carré correspondence. So this works quite well. This is two of the three problems, the identification, the translation. Now we have to talk about combinations of theories, the co-limits, because there's a general notion that if you talk about those three questions, you are talking about a category. That's not quite accurate because, well, you could say that identification is just the objects and the isomorphisms instead of a category, and the translations are morphisms, and that combinations are just co-limits. But that doesn't work quite well because logics are kind of stretchy, let's say. You can replace terms with equivalent terms, and that looks like homotopy. And there are people that argue that we should look at theories which are more homotopic in nature and not really categories, but it doesn't matter. The point is that combinations have the general flavor of co-limits. So to look at an example, I'm not going to give the definition because it's quite technical and not very insightful. To look at an example, let's say we start with the theory of monoids and we interpret it inside of the theory of sets, which you'll notice I have not included here because here I have not included the declarations of a theory of sets. These are just the terms that are translated, but you can imagine it would look something like ZF. It doesn't matter. What matters is that we interpret them into sets, and then we extend the theory of monoids into a theory of groups by adding a notion of inverse and the axiom that the inverse is really an inverse. Then we can do a push out of this diagram. The diagram, again, that is composed of the theory of a monoid going to the theory of sets and into the theory of a group. And the theory would look like the theory of a set with two additional declarations, which says that for that particular type set we have constructed, there is an inverse notion of inverse to its end of functions, and that it's really an inverse. And if you wanted to really find a set which looks like that, you would need to implement that theory. So again, we're looking at theories like interfaces. Does MMT implement universal logic? Well, kind of. It needs some modifications, but generally, yes. We can talk about identification by talking about the objects and isomorphisms. Translation is just morphisms, and the combinations are push forwards and finite colimits in general. Not all colimits exist in MMT as it is defined in the literature, but we can, I believe, modify it to make it more general. Anyway, this is just a large introduction to what I want to show you. Are there any questions before I proceed?
No, there don't seem to be any questions at this point. Thank you.
Okay, great. Now I want to show how would modular mathematics be done. What would it look like? I want to look at the notion of phi, the fundamental group of a topological space, and how we would go about formalizing it inside of a system similar to MMT, using the ideas of universal logic. So here are the basics. We are talking about groups and we are talking about topological spaces. I'm not talking about how we would come to the insight of the fundamental group. That's beside the point. I want to know how to formalize it in this modular way so that perhaps we can have more insights on it. I just want to show how it would work inside of this theory. So we start by defining two theories, a theory of a group and a theory of a pointed topological spaces, which is necessary to talk about topological spaces and groups. The theory of a group looks like what you would expect. We have a type of points, we have a product, we have a neutral element, an inverse, and then four axioms. And similarly, the theory for a topological space is given by a type of points, a family of open sets, a base point, such that open, you can think of open as a predicate. The power set is just a predicate on elements. So we are saying that that predicate is valid over the full space, over the empty subset, that for an arbitrary union of open subsets, we have an open subset and the binary intersection. This is just the usual way we do topology, basic topology. But then I want to talk about categories because it's pi 1, it's a functor. So we need a way to talk about categories. And look, what we are doing, observe that what we are doing is just defining the vocabulary to talk about the subjects. It's nothing serious. It's just the way we usually do stuff, and then the rest falls into place. So category is given by a type of objects, a type of arrows for every pair of objects, an identity arrow for every for every object, a notion of composition, and that satisfy three laws, which is associativity and the two identities. If you look at a library for example, the programming language Idris, which implements categories, you will find something similar to this. This is pretty standard. We're just translating it into MMT. And then here comes the novel way to think about things. Because categories, because theories are interfaces, when we want to define an interface, define a category, we just implement that interface. But where? Because take a look. This is not the theory of groups. This is the theory of a single group. Because the models of this theory we expect would be groups, single groups. And if we want a theory to talk about multiple groups, then we need to transform this theory into a theory of the collective of all groups. So here's the process I call collectivization. We take a theory, remember, it's just a sequence of declarations. And we choose a name for the collective, and then we transform the theory, the original theory, the sequence of declarations here on the left, into another theory which starts with a declaration of a type for the collective of the structure of that theory. And then for every declared name in the original theory, we transform it to take a parameter in that type, the type of the collective. What is written here is just take every declared name and put a little parameter C. So if you have a name, a declared name B, then you put a parameter. And if you have a constructor being applied to some expressions, you just apply that constructor to the morphism applied to some expressions. Again, the expression here is more complex than the idea. Let me show an example and it will be clear. Here is the theory of a group on the left and the theory of the collective of groups on the right. You see that all of the declarations are here, but they are modified. First, at the start, we put a declaration of a type for a group, for the collective of groups, which I call GRP. And then we add a parameter for every declaration. So here on the left, you'd read, well, point is a type, the dot is a product between points of that type, E is a neutral element. And here you read, group is a type. For every group, we have a type of points. For every group, we have a notion of a product between points of that type of points, which is why we have a little parameter here, and etc. It all works out. But then, here comes the magical bit. We can interpret the theory of a category inside of the theory of the collective of groups, thereby showing that groups form category, or constructing a category with groups as the objects. How would we do it? Well, we just translate the theory of a category in this way. We say that the term object goes into group, which are both types. We take the function arrow and we associate it with the type of the, this is just a shorthand. You actually send arrow to lambda g, lambda h, doesn't really matter. We're defining arrow as this function. But look, this is all just translation. I'm not defining in terms of, I'm not equating anything. I'm not doing mathematics in the usual way of doing it semantically. I'm just doing translations. And then, as I said, the axioms would go to proofs that the properties, the relevant properties are satisfied. We do the same for topological spaces, and then we come to the crux of the matter. I've thought of 3 ways to implement Pi1, which go from the least to the most idiomatic inside of MMT. Let's start with the least, which is the internal functor, just the way we do it in mathematics. I will explain the diagram. We construct a theory where we can do mathematics. So we start with the category of groups, which is this arrow on the left, category of topological spaces, which is this arrow on the right. Then we interpret the theory of a category inside of the collective of categories with a distinguished point, which is to say, look, if we take the collective theory of categories with a distinguished point, then that distinguished point is actually a category. And if we take the co-limit here, we end up with 2 theories, the bottommost dots, bullets, which are theories that allow us to talk about a collective of categories together with a single category of groups or of topological spaces. So when we combine them both, we end up with a theory that allows us to talk about a collective of categories with 2 distinguished categories, one of groups and one of point topological spaces. And then we have all the tools of type theory, so we can define what is the type of functors, and we can construct an instance of that type, which is the functor type. But this is just the usual way we do it in mathematics. It's not interesting to go all the way to build MMT and the theories, etc., and just do it the traditional way. There are more idiomatic ways to do it. Here's just some details on how we would build that functor. We would declare the object part of the functor and construct a type of the element functor between the two categories which are internal to that theory, and etc. Just so this section is quite large, so let me ask if there are any questions about the details.
No, there aren't any questions. Thank you.
Okay. So this is the second way. Let's remind ourselves what we are doing. We are doing inside of this modular framework. We're trying to formalize pi1. We have seen one way to do it. Now I'll show you another way, which is not the same, obviously. This is the way in which we would define a theory of what it means to be a functor. So what is a functor? A functor is something defined over the vocabulary of the collective of categories. To be able to talk about functors, you need to be able to talk about a multiplicity of categories. So we take the theory of a category, we take the collective of it, and then we extend that theory, because again, a theory is just a sequence of declarations. So we can append declarations to a previous theory. And we say that a functor has a source, has a target, has a function on objects, has a function on arrows, and has a notion of functoriality or coherence. It respects the structure of category. So if you think of this theory as an interface, this means that we would interpret, to interpret that theory means to interpret the collective of categories inside of another theory, and then interpret a single functor. Choose a source category, choose a target category, and choose all of the structure that defines a functor. Then we can just do it. Interpret functor inside of a theory, which allows us to talk about the category of groups and the category of topological spaces. Then the term source is interpreted as the category of topological spaces, this term target as the category of groups, and etc. Here I've just put a note that says, what is this theory we're talking about? But you can think of kind of co-limit where we take the vocabulary of groups, the vocabulary of actually the morphism of the category of groups and pointed topological spaces, and we combine all of it to be able to talk about them both. It's the theory that's on the top of the diagram. So this is the second way. It's more idiomatic because we are formalizing pi1 as a translation from a theory of functors to a theory of some special categories. So we are saying that it's a translation, it's an implementation of the notion of functor. But more directly, I'd say that what is actually done in the fundamental group is that we are translating topological notions into group theoretic notions. So this is the third way, the translation. We translate. Now, see, this is contravariant because we are interpreting the theory of groups inside of a theory of topological space, and not the other way around. So we actually interpret the theory of a single group inside of the theory of the collective of topological spaces with a distinguished point. So how would we do it? Well, we interpret point, the type point of the group, as the type of paths that start and end at the base point, quotients by the traditional equivalence relation between reprogrammized homotopical paths. And the product is interpreted as composition, and identity neutral element is interpreted as the constant, the class the equivalence class of the constant path, and etc. And here again the beautiful thing, the axioms, the statement, the name of the axioms must be interpreted as proofs that they hold inside of this vocabulary, this domain of discussion. So I have shown you 3 ways to formalize Pi1. What's the purpose? I'm trying to show you what modular mathematics could look like. It should aim to implement tools organized by universal logic in a way that allows us to build synthetic theories of different areas more easily, to combine, to transform them. It doesn't solve the problem for you. Just like category theory, it doesn't solve any problems for us most of the time. It serves as a guide to structure our thoughts and our investigation. So when we are interested in a class of objects, we intuitively build categories out of them and morphisms, and then we can ask, what are the good properties of this category? What limits exist? Have this function? Does it have an adjunct, etc.? It guides the way we can think. And what I'm saying is that a theory with the spirit of universal logic can be kind of a structuring theory to synthetic reasoning. What is missing here? Well, basically the full formalization of the variant of MMT that will implement universal logic, and an investigation of the categorical structure of those transformations which I showed you, like collectivization and a collectivization with a distinguished point. What universal problems does that solve? And if you have a categorical understanding of the category of theories, then that's better justifies what we are doing there. It orients us into the ways we can transform and look for synthetic theories. What is the synthetic theory that solves a particular universal problem? So this is where I'm at, and this is where I'm going. And that's it. Thanks. So
thank you very much.
Questions?
Yes, so everyone is welcome to type questions into the chat, and you can type them just to me if you want, but there are already some questions, so I'll start posing some questions. And so one question says, what were the challenges that prevent MMT from having all of the expected co-limits? Is it a computability thing, or is the language just not rich enough to express them?
It's just not rich enough, because as you can see here, the co-limit I have here, as you can see, MMT is built upon a notion of category with inclusions. So it's a category with a distinguished class of monomorphisms, which are special in some way. Here you can see this is an inclusion. An inclusion is just an extension. It's what I said when I...
Are you showing us something on your screen that we can't see at the moment?
You can see? Well, I was...
because I shared.
You stopped sharing.
Yeah.
Okay. I can't find Zoom. Actually, I can see you. Here.
Share your screen again.
I wasn't finding the window. Share screen. Here. As you can see in the slide here on the left, the arrow is an inclusion. It has the curvy bit at the tail. And this is just a regular morphism. And here we have a regular morphism. This is just a theory extension, which is appending stuff at the bottom. The co-limits are defined for these kinds of inclusions because, well, the problem is that in this kind of co-limit, it's easy. You just have to substitute into some variables some terms that were translated. But when you go to talk about general co-limits, then you have to do identifications on the on the other side. You have to, it's analogous to when you do first order logic, you have a signature, or let's say equational logic. You have a signature, and then you have equations on that signature. The theories in MMT are just signatures. They don't have equations. And that's the missing bit, which I'm not sure if it should be introduced as just equations, pairs of terms, or inside of the axiomatic system, the inference rules. I'm not quite sure, but that's something that has to be worked out.
Okay, here's a question. Is there any relation between universal logic and universal algebra? And
yes.
Yeah, go on.
Well, at least there is a relation between the names. One description I read is that universal logic tries to do to logic what universal algebra did to algebra. So the name it's literally an analogy. There aren't really any formal links besides the usual links between logic and algebra. But yes, it's an analogy.
And then another question, is there a connection between universal logic and Gergen and Burstall's institution theory?
So institution theory, if I'm not mistaken, yeah, they actually come from the same motivation. So the institutional framework of institutions, they talk about the proliferation of logical systems in the 70s in the world of computer science. And they're trying to, I'd say that institutions are an attempt to attack the problems of universal logic. It's, again, universal logic is not an open problem. It's a research program, so you can't really say that it's solved or that you're attempting to solve it. But I'd say that institutions are one way of looking at universal logic, of organizing logics. I personally don't think they really answer the question of what is a logic, because, okay, institutions deal with logics in a categorical way, so structural. They talk about what a logic has to be able to do to be a logic, and okay, it works, but it's a bit too semantical to my taste. I don't think, again, as I've said, I think models are just translations, so I don't think we should formalize logic in terms of interpretations in the model theoretic sense, but that's just my opinion. It's all related, obviously.
Thanks. And there's a slightly off-topic question, but someone says, what font is that?
This is E.B. Garamond. It's an open source variant of the traditional Garamond font.
Thanks. Does anyone else have any questions? If there are no more questions, let's thank the speaker again. Hooray. Thanks very much. If anyone would like to reveal themselves and say hello, then you're welcome to do that. At this point, should we stop the recording before we do that?